let us recap what we have studied so far. We know that the three-phase induction machine contains three-phase windings on the stator, phase A, phase B and phase C, and they are separated by 120 electrical degrees from one another. If a constant current excitation is applied to the winding of any of the phase A, phase B or phase C, a space sinusoidal MMF will be produced in the air gap. On the other hand, if a sinusoidal excitation to any of the phase A, phase B or phase C is applied, a standing wave space sinusoidal MMF or flux will be produced in the air gap. And finally, we've seen that if the three-phase windings A, B, C are excited by a balanced three-phase sinusoidal source A, B, C, then a rotating MMF or a rotating flux will be produced in the air gap. And we have seen these animations in the previous lecture. The frequency of the rotating flux, which is produced by the three-phase excitations on the stator windings A, B, C, is given by this equation, where P is the number of poles, F is the supply frequency, and this frequency is known as the synchronous angular frequency, or just simply synchronous frequency, and also sometimes known as the synchronous speed, if it's referred to the speed of the rotor. Sometimes the synchronous speed is also written in terms of the rotation per minute, RPM, and it is given by 120 times F, which is the supply frequency, over P, the number of poles. For example, for a 50 Hz system, if P is equals to 2, which means that the number of poles is 2, then Ns in RPM is equals to 3000, and omega S, which is the synchronous frequency, is equal to 314.16 radian per second. If P is equal to 4, then Ns equals to 1500, omega S is 157.08. If P is equals to 6, then Ns is equals to 1000 RPM, and omega S is equal to 104.72 radian per second. These are the synchronous frequencies for 50 Hz systems, which is the frequency of the supply in our country. Now, this rotating flux, which is caused by the excitations on the stator windings, will induce EMF on the stator. This EMF induced on the stator is known as the back EMF, or air gap voltage. The magnitude of this induced voltage will depend on the frequency of the supply as well as the magnitude of the rotating air gap flux. The same rotating flux is also going to induce EMF on the rotor. Assuming that the rotor is rotating at some speed, then the frequency of the induced voltage on the rotor will not be at F, but rather at slip frequency, which is the difference between F and the frequency of the rotating rotor. If the rotor is shorted, which is true for squirrel cage type of rotor, or if it is a wound type rotor, then if we shorted the end connections of the windings, then rotor current will start to flow, and this rotor current will produce rotating flux, which is caused by the rotor current itself, and it is called the rotor flux. The rotor flux will rotate at a slip frequency relative to the rotor frame, which is rotating. Therefore, relative to the stationary frame, this rotating rotor flux will be at a synchronous frequency, which is at the slip speed plus the rotor speed. It is important to understand that the EMF on the rotor is only induced when there is a difference between the rotating flux speed and the rotor speed. In other words, in order for the EMF to be induced on the rotor speed has to be less than the rotating flux speed. Which means that if the rotor rotates at the synchronous speed, then there will be no induced voltage on the rotor circuit. The rotor rotates when there is torque. The torque is produced when there is an interaction between the air gap flux and the rotor flux. However, we have seen earlier that in order for the rotor flux to be produced, the speed of the rotor has to be less than the speed of the rotating air gap flux, which means that in order for the torque to be produced, the rotor has to rotate at a speed which always less than the synchronous speed. And the difference between this synchronous speed, which is the speed of the rotating air gap flux, and the rotor speed is known as the slip speed. The ratio between the slip speed and the synchronous speed is known as the slip. We are now going to develop the equivalent circuit for the induction motor. We know that the induction motor is a balanced three-phase system. Like other balanced three-phase system, it is therefore sufficient for us to develop an equivalent circuit for just one phase, which is what we call the per-phase equivalent circuit. The frequency and the magnitude of the voltages and currents for all the phases are going to be the same. The difference is only going to be on the phase angles of these voltages and currents. We start off with the stator voltage equations. Vs is the applied voltage, which is a phase voltage. RSIS is the voltage drop across the stator resistance. And 2 pi f LLS times IS is the voltage drop across the leakage inductance, and EAG is the back EMF voltage, which is the voltage induced due to the rotating flux that we have seen before, and it is given by this equation here. The leakage inductance drop is to account for the flux which does not contribute to the rotating flux. Similarly, for the rotor voltage equations, we write down the balanced rotor voltage equations by equating the induced voltage on the rotor circuit, ER, equals to the voltage drop across the rotor resistance plus the voltage drop across the rotor leakage inductance. Notice that the frequency of the induced voltage on the rotor is at slip frequency FSL. The two equations here cannot be combined because they have different frequencies. In order to combine the two equations, we need to multiply the second equations with F over FSL. If we do that, then we end up with these equations here. Using these two equations, now we can develop the per-phase equivalent circuit of the induction motor. This is the per-phase equivalent circuit of the induction motor. It is developed based on the equations that we have derived before, which are the stator voltage equations and the rotor voltage equation. If you look closely to this equivalent circuit, you can see the similarity with the per-phase equivalent circuit of the transformer, which you probably have seen or studied before in your previous course. Lm is the magnetizing inductance, which is used to represent the inductance that is responsible in producing the rotating flux in the air gap. Im is the magnetizing current, which is responsible in producing the rotating air gap flux. This is the ideal transformer. Unlike the transformer per-phase equivalent circuit, in the induction motor per-phase equivalent circuit, the secondary voltage, which is the rotor voltage, depends on the speed of the motor. We can remove the ideal transformer from the equivalent circuit by using the referred quantities. For example, if the rotor parameters and variable are to be referred to the stator, then we can use this transformation equation in order to transform the rotor parameters and variable to the stator. If we substitute the transformation equations into the rotor voltage equations, then we can write down the rotor voltage equation as shown here. Finally, we obtain the per-phase equivalent circuit for the induction motor with the referred quantities. This is the IEEE recommended equivalent circuit for the induction motor. In this equivalent circuit, the core losses is lumped together with the windage and friction losses, which is known as the rotational losses. We will use this per-phase equivalent circuit in analyzing the performance of the induction motor. When we supply the three-phase stator with a voltage supply, we are supplying the input power to the induction motor. We know that there is no physical connections between the stator and the rotor. Therefore, the power that goes to the rotor circuit from the stator circuit is via the air gap, and this power is known as the air gap power. The only active power which is involved in the rotor circuit is due to the rotor resistance shown in this diagram here. Therefore, we can write down the air gap power as equals to 3 times IR squared times RR over S. We use the multiplier 3 because we are representing the air gap power as the total power due to the three phases. The air gap power can be separated into two terms as shown by these equations here. The first term here represents part of the air gap power lost due to the rotor resistance winding, while the second term here represents portion of the air gap power which is converted to the mechanical power. As you can see here that the amount of the air gap power which is converted to the mechanical power depends on the slip S. The smaller the slip S, the more air gap power is converted to the mechanical power. This is the reason why the induction motor is normally operated with a small slip, to make sure that most of the air gap power goes to the mechanical power, which is used to develop the torque. We will now do example 5.1 and 5.2.